In this video, we have to solve a first-order system of ODEs. We have this system of ODEs where U contains two components, U1 of t and U2 of t, and U prime contains the derivatives of U1 with respect to t and the first derivative of U2. It's first-order system because we have first-order derivatives. The general solution for this kind of problems is given by this formula. C1 is just an arbitrary constant times e to the power of lambda 1 times t, v1, where lambda 1 is an eigenvalue and v1 is the eigenvector, plus c2 e to the power of lambda 2 times t, v2. I will explain what are the eigenvalues and the eigenvectors here by first writing this system of ODEs in the following way. U prime equals A times U. A is called the coefficient matrix because we have the coefficients here, 1, 2, 2, and 1. This is the coefficient matrix. So lambda 1 corresponds to the first eigenvalue, lambda 2 the second eigenvalue, and v1 is the eigenvector associated to the eigenvalue lambda 1, v2 is the eigenvector associated to the eigenvalue lambda 2. C1 and C2 are just the real coefficients, arbitrary coefficients. In order to find the explicit solution for this system of ODEs, what we need to do is to first find the spectrum of this matrix, which means that we need to find the eigenvalues of this matrix. Finding the eigenvalues. We form this matrix here, which means that in the diagonals we have 1 minus lambda, 1 minus lambda, and here we have 2. The characteristic polynomial is the determinant of this matrix of A minus lambda I. This can be written as lambda minus 1 squared minus 2 squared. This difference of 2 squares, so I can use the known identity. Like this. This first bracket is lambda minus 3 times lambda plus 1. And I take the characteristic polynomial to be equal to 0. So the roots of this characteristic polynomial are my eigenvalues. Lambda minus 3 is equal to 0. Lambda equals 3. This is lambda 1. Lambda plus 1 is equal to 0. Lambda equals minus 1. And this is lambda 2. Now I need to find the eigenvectors associated to these eigenvalues. The spectrum of this matrix is lambda 1 and lambda 2, the two eigenvalues, 3 and minus 1. Now I need to find the eigenvectors associated with these eigenvalues here. Let's take first with regards to the eigenvalue lambda 1. I need to solve this linear system of equations. What was lambda 1 was 3, the first eigenvalue. The first was 3 and the second minus 1. From here I have 1 minus 3, 2, 2 and 1 minus 3. And this is xi1 and xi2. From here what I obtain is that xi1 equals xi2. My eigenvector is xi1, xi2. Xi1 is xi2, so I can write it as xi1 times 1, 1. And if I put xi1 equal to 1, my eigenvector is 1, 1. So this is finding the first eigenvector. And here finding the second eigenvector. 1 minus lambda 2 xi1 xi2 equal to 0. We said that lambda 2 is minus 1. 1 minus minus 1 gives me 2. So I get a matrix where all the elements are 2. And from here I just obtain an equation involving xi1 and xi2. So the sum of xi1 plus xi2 is equal to 0. And here I solve for xi2 equals minus xi1. The second eigenvector will take the following form. Plugging in xi1 to be 1, v2 is 1 minus 1. Now that I have everything, I can explicitly write down my solution. U equals C1 times E. Let me write again the formula. V1 plus C2 e to the power of lambda 2 times t, V2. Lambda 1 equals 3, lambda 2 is minus 1, V1 equals 1, 1, the two eigenvectors, V2, 1 minus 1. C1 e to the power of 3 times t times my first eigenvector, e to the power of minus t times the second eigenvector. This is my general solution. Where these two coefficients are real. Or I can write it in this way, u1 of t, u2 of t equals c1 e to the power of 3 times t, the first eigenvector, plus c2 e to the power of minus t, and the second eigenvector,